On a hot September afternoon in 1970, a high school football team in St. Petersburg, Florida was running a normal practice. No rain, no dark clouds, just heat and humidity. And somewhere in the distance, a low rumble of thunder. The offensive unit broke into a huddle to call the next play. Then, lightning struck. In an instant, players and coaches dropped where they stood. 2 were killed. More than 20 others were injured, some seriously. Nearly 40 people taken down by a bolt none of them saw coming. That moment changed how schools across the country think about lightning safety, because it proved something that still catches people off guard today. You don't have to see it to be in danger. Today we're going off the radar to learn about one of nature's most powerful forces. We'll debunk some of the safety myths many of us grew up believing.
Metal does not attract lightning.
We'll meet the scientists tracking record-breaking megaflashes and why the most dangerous ones often strike after you think the storm has passed. I'm meteorologist Emily Gracie, and you're listening to Off the Radar, a production of the National Weather Desk. On the show, we dig deep into topics about weather, climate, the ocean, space, and much more. Our goal is to help you better understand the weather and to love it as much as we do. Hi, everyone, and welcome to Off the Radar. We have some pretty cool episodes coming up in the next month, covering topics like severe weather research, earthquakes, environmental impact stories, and hurricane stories. So do me a favor and hit the follow or subscribe button so you know when that new episode drops each Tuesday. Today we're digging into lightning. First, I'm joined by John Jensenius, a lightning safety expert who has spent years studying how and why people get struck. He breaks down what actually keeps you safe. A few of his answers actually surprised me. Then I'll talk with Dr. Tim Logan from Texas A&M, who runs the Houston Lightning Mapping Array Network. He's helped discover 2 of the longest flashes ever recorded on Earth. He walks us through what scientists are learning right now and what still baffles him as a lightning scientist. John Jensenius, you are the lightning guy. In fact, I've heard you referred to that way. I think if somebody in the weather community said, you know the lightning guy, you would say, yeah, it's John. So tell me about lightning as a hazard and where it kind of stacks compared to other weather hazards.
Well, it's kind of an interesting question because in terms of the hazards, lightning is probably the one that is that most people see every year, at least once, and oftentimes many, many times throughout the year. So it is a hazard that most people in the United States have to be aware of and have to be concerned about. In terms of the number of people that are killed by lightning, fortunately, we've seen the number of deaths go down. At one time, it was considered the second leading cause of death. It's down the list quite a bit since we started the lightning campaign about 25 years ago.
So do you think it is a matter of awareness?
I think awareness plays a large part in it, first of all, making the public aware, but also making people that run organizations aware of the dangers of the lightning, and then making sure the policies of those organizations reflect the dangers that lightning poses.
Okay, so tell me some stats, because I know there's certain things like times of year, states, and then also like activities that are being done when people are impacted by lightning.
Well, since 2006, I've documented over 500 lightning deaths in the United States, actually 517. Of those 500, over 328 have been caused by people enjoying outdoor activities, things like fishing, boating. So it's those outdoor leisure activities which tend to cause the most deaths. In terms of what we call the deadly dozen, fishing is number 1 on the list, followed by things like boating or going to the beach. In terms of work activities, it's things like farming, ranching, or roofing. Those are the ones that tend to cause the most lightning deaths. But anytime you're outside, it's dangerous when a thunderstorm is in the area. And when we say a thunderstorm is in the area, we mean anytime you can hear thunder or it looks at all threatening, at that point, it's time to get inside because the lightning can strike up to 10 miles from a thunderstorm. And if you're hearing thunder, you're likely within that 10-mile limit. Across the United States, areas that have the most lightning tend to get the most lightning fatalities, but that's not necessarily the case. So if we look at places like Florida, along the Gulf Coast, Texas, they get a lot of lightning, and up through the Mississippi Valley gets a lot of lightning as well. So that is one of the factors that is important in terms of the number of casualties we see. But the other factor is outdoor activities. So anywhere where people are outside, for example, a place like Colorado, you see a lot of lightning deaths as well, just simply because there are a lot of people outside enjoying summer activities. In terms of the time of the year, we've seen people struck and killed every month except December. So anytime throughout the year. But the most dangerous times are the times when you have lightning and outdoor activities. So the lightning is starting to increase as we go through the springtime into the summer. The people are enjoying more outdoor activities as we get to summertime when they have time off, taking vacations. And it's that combination of those outdoor activities and the amount of lightning that leads to our greatest number of deaths.
Is it true that way more men get struck by lightning than women?
We found that about 80% of the fatalities are men. And there are several reasons for that, at least what we think. First of all, men tend to be involved in more vulnerable activities. And I mentioned a couple of those, fishing, for example, and boating. And one of the reasons that those particular activities are particularly dangerous is the fact that you may be a long way from safety. And if you're a long way from safety, it's going to take you longer to get inside a safe place. So the important thing to remember is if you're involved in one of those activities where you're going to be some distance from safety, first of all, check the weather forecast. If thunderstorms are forecast, make sure you can get to that safe place very quickly, or just simply cancel or postpone the activity. If you are out there, you have to pay very close attention to any signs of a developing or approaching thunderstorm. And when I say any signs, I don't just mean keeping an eye on the sky, but that's also important too. But monitoring weather conditions via weather apps, radar, lightning apps, anything you can that would give you information on an approaching or developing storm.
What are some common myths that you hear when it comes to lightning safety, or some rumors you'd like to dispel when it comes to lightning?
Well, probably the most common myth is the myth that metal attracts lightning. Metal does not attract lightning. It will heat up. It will leave burn marks if you've got metal in your pockets or you're wearing any jewelry. It will heat up and cause a burn mark. And oftentimes that people interpret that as it's attracted lightning, but it really doesn't. Lightning tends to strike the tallest object in the immediate area. Oftentimes that's a tree, but if you're out in the open, that could be you as well. Now, one of the things that people are concerned about I say, don't stand under a tree, don't be out in the open. Well, you shouldn't be any of those places because you really need to be inside. But if lightning strikes a tree, it's important to remember that lightning, that charge is going to spread out along the ground, something we call ground current. And that ground current is just as dangerous as a direct lightning strike. In fact, we think more people are killed by ground current than direct lightning strikes.
Wow. Okay. And something you did a talk, I think it was in Boise at the AMS broadcast meeting, where you were talking about what you do if you are like out in the middle of a field with nowhere to go during the lightning storm. And I think as a child, like I was taught one thing, but you were saying like run, right?
If you're out in the open, there really isn't anything you can do to prevent being struck by lightning. So our recommendation is run as fast as you can toward a safer place. A typical thunderstorm, if you consider from the time it becomes dangerous, which is when it's approaching, to the time it's gone, well gone, and is no longer dangerous, is an hour. So, for example, if it takes you 20 minutes to get to a safe place, you've already cut the odds of being struck by 2/3. So you only have 1/3 of the chance of being struck if you can get to safety in 20 minutes. That said, hopefully you can get to safety even faster than that. So it's important to get to that safe place, because that's really what you need to do if a thunderstorm is in the area.
So don't crouch up and make yourself into a ball like we were taught when we were kids.
No, we don't recommend that anymore. That is kind of a old, I won't call it a myth, because it was believed at one time to reduce your chances of being struck. But really, it really doesn't make that much of a difference when it comes to lightning. If it's not striking you directly, it's striking near you, and you're vulnerable to the ground current, whether you're crouching or not.
You talk about lightning deaths, but what about non-deaths? Like, what can happen if you get struck by lightning and you don't die? Are there long-term impacts there?
Well, we look at it as several layers. First of all, the first layer is immediately after you get struck. And if somebody is struck, the most important thing is to initiate CPR if they need it. If there's an AED available, that's important as well. And call 911 to get help immediately. So hopefully help arrives quickly. But in terms of the effects that we see, oftentimes if somebody is initially struck, they're unconscious. When they do wake up, they may not know what happened, probably don't know what happened. They may have dizziness. They may be vomiting. Those are some of the immediate effects of being struck. But in terms of long-term effects, it oftentimes affects the person's personality, his ability to process information, to save things in memory and then recall things in memory, can be associated with long-term pain. There's a whole list of things that are very unfortunate for even the lightning survivors.
When it comes to awareness, I would guess that the non-English speaking community is probably pretty impacted by lightning. Is there effort in that respect to put out the same awareness information in other languages?
Well, we try to get information out in Spanish. And when I say we, the National Lightning Safety, as well as the National Weather Service, try and get information out to the Spanish-speaking community. I will say it is a little more difficult because many of the members of our teams, or in fact, most of the members of our team don't speak Spanish. So we have to rely on help from the outside to get some of the information out there. But it is very important because there are a lot of Spanish-speaking individuals in the southern part of the United States where we do see more lightning, especially some of the construction and roofing workers often are Spanish-speaking. So we do try and get as much information out in Spanish as possible.
John, is there anything else you want people to know about lightning as we head in towards this severe weather season?
If you're planning an activity, check the weather forecast. And if thunderstorms are predicted, consider canceling or postponing the activity. If you do go out, monitor weather conditions, keep an eye on the sky, listen for thunder. If you do hear any thunder, you need to get inside immediately. If you see signs of a developing or approaching storm, you need to get inside immediately. Once you are inside, there are things to remember is that if the building is struck, and I should back up and say when I say inside, I mean inside a substantial building, not a shed, a building that has wiring and plumbing. If you are inside that substantial building, you want to make sure you're not connected in any way to a wire. So anything that plugs into the wall is dangerous. And you want to stay away from any plumbing. So you don't want to be doing dishes or washing your hands. It's important to know that you have to wait 30 minutes after the last lightning or thunder before going back outside because there are lingering charges in the atmosphere. So we have a very simple saying, when thunder roars, go indoors. If you hear thunder, you need to get inside immediately. And you remain there for 30 minutes after the storm has passed.
John Jensenius, the lightning guy, thank you for all of the information today. This was very helpful.
Well, thank you, Emily.
Dr. Tim Logan, thanks so much for joining me today to talk about lightning. We met at AMS in Houston this year. We talked about lightning, and I, learned over cocktails that you made some discoveries when it came to lightning. So I can't wait to hear all about those today. Can you tell me a little bit about like your role at Texas A&M and what your research really is focused on?
Yes, I'm an associate professor at Texas A&M University in the Atmospheric Sciences department. And I got here, I guess, in 2014. I had just went back, I don't know if recently is the word, but I went back to school, non-traditional student, to get my master's and PhD at North Dakota. And from there, I wanted to teach college. I used to be a high school teacher for a while in New Jersey. And then I was like, yeah, I would like to teach college at some point. So what I started out with my studies was actually not lightning. It was kind of something related, only because it was a hobby more than something that was research worthy. At least that's what my advisor had said. But I actually studied what's called aerosols. So these particles that move around in the atmosphere from place to place, and they impact how clouds develop. And of course, lightning comes from clouds and storm comes from clouds. So I was making a connection between how aerosols can impact how storms form, precipitation, things like that. And the whole quote unquote storm chasing thing that I did as a grad student, which was frowned upon. But
Really?
it was a way to kind of visually say what I'm doing in terms of my research.
Gotcha. Okay. When I used to do school visits or when kids find out that I'm a meteorologist, I would say one of the biggest questions I get asked is about lightning and thunder and what's happening there. Can you give me like your basic version? Because we have a lot of like non-science listeners to the podcast of what's going on here, how lightning happens, where this sound comes from, what's actually happening in kind of like layman's terms.
With lightning, so lightning is actually evidence that there's ice in a cloud. So if there's a thunderstorm that's going on, it's doing a lot of rain and things like that. If there's ice, then that's a telltale sign that you should have some type of lightning. There's other things that are going on in there, like liquid water finding itself below freezing. So we call that supercooled liquid water. And then the ice particles just basically crash into each other because it's so turbulent in a thunderstorm, and they create charges. So the little ice crystals go up to the top of the cloud. The big ice crystals go to the bottom. And then that's how you get your charge separation. And, nature doesn't like differences from, 2 points like that. So the lightning kind of balances everything out. So all of those ingredients come into play. But my first week as a grad student in North Dakota, that we were assigned a homework problem set that was due on Monday. And then Sunday night, surprise, surprise, like, this is why you should always do your homework when you're supposed to, not wait till the last minute. But Sunday night, this big storm comes through. And it dropped a couple of tornadoes south of campus. I mean, it was too close for comfort. But since a few of us didn't get our problem set done on time, we really couldn't go chase with the other students. So we were stuck at the office trying to solve problems, get the homework set done. But we noticed that for 3 hours straight after the storm had passed, it was just a strobe effect of lightning that was going on. And it's something I've noticed before, I guess in the past, that you have these storms and you see the lightning crawling across the sky, after the storm has passed, because you could just go outside and take a look. But this was popping, for, like I said, 3 hours about. And that always intrigued me because I'm like, what's going on? And I'm like, if I ever get, my hands on some data and really figure out what's going on, I'm going to write a paper about this. And this was back in 2007. And I did end up writing a paper, which kind of catapulted me to where I am now. But that came out about 10 years later when I finally got the story together. But it's something that, and again, it's part of what I studied as a grad student, that there was an aerosol effect. There was some smoke that drifted into the area, and that actually interacted with the thunderstorm, kind of juiced it up. So I wrote a paper on explaining the processes with that. So it's not a new concept. It's just finding it in nature to apply to. So all of these connections, I love connections, because one thing kind of leads to another, kind of leads to another, kind of leads to another.
Okay, well, take me back to your research and kind of over the past few years, you've made these discoveries when it comes to longest lightning strikes. So I guess my first question is like, what does longest mean? Are we talking about time duration? Are we talking about length across land? How do you measure this?
There's actually two, and you brought them up. So time is one thing. There's a record for longest duration. So as the lightning kind of traces a path across the sky, it's just sitting there illuminated for several seconds. And I believe that one is 17 seconds, and that was set in South America, I believe. So imagine, if had it come to ground and, God forbid, hit somebody or hit something, that's 17 seconds that you just sitting there stuck. But extent is the actual aerial distance of the lightning bolt. So again, you see the spider lightning go across the sky, but that's only a little piece. It turns out that's only a little piece that we see. It could have come from miles away, or in the two cases that I worked with, hundreds of miles away. And it's one of those things that you're not really looking for it, especially with the lightning platform that I have. It's more ground-based, but satellite is able to see the bigger extent of the flashes as long as it's looking in that area and can measure it at the time that it happened. So it was two independent reports that basically saw these. So there's three. I count three, actually. Four now. The first one was within what's called a lightning mapping array network, which is a bunch of sensors that just listen for the little pops of electric pulses that come from lightning. So those are lightning mapping arrays. And then the optical detectors will sit there and take a picture of the entire lightning flash as long as their field of view is wide enough. So that's what we have on satellites now. So the very first one was around, and I gotta speak English instead of metric, right? But it was around 200 miles was the first one. And then the second one was closer to 400. And then the one after that was the one I was part of, which happened here from basically from southwest of Houston to just west of Mobile, Alabama. So that one was the third longest extent. And then the brand new one that we actually went back in the data for 2017, that one stretches from just south of Dallas to just east of Kansas City, Missouri. So that's the current longest one now. And we see these only because we have the detectors capable, like I said, wide field of view. And we can kind of see it as it progresses from one point to another. But what my sensors that we can tell if it started at point A and went to point B versus point B to point A. So that's sometimes satellite will have issues with verifying that. So you need a bunch of people on these committees, to sit there and we go back and forth and we just discuss, is this real? How do we validate it? And then submit it, and there we go. And it turns out, just real quick, they happen all the time. It's just now we have better technology, and they're just popping out all over the place.
I was going to say they're records, but they're all recent because this is like new tech, right? But you can go back and look at old events on satellite as well. Is that part of your research, or are you more focused on like what's happening now and in the future?
It's mainly now. I wear several hats, but what's going on. But the long extent lightning or the megaflash is anything greater than 60 miles. We see these long extent flashes a lot around the Gulf Coast and around Houston, for sure. But again, it's usually where the storm is passed and they pop out on the back end where it's not raining as much. And that's what makes these storms so dangerous, is because you think the rain has stopped, you can see a little bit of stars, or maybe if it's during the day, sun's trying to come out. But if you still hear that rumble of thunder, those long extent bolts, that's what's going on. You can't see them until they come to ground. But the storm is miles away.
When people use the term bolt from the blue, is that this type of lightning, or is that something different?
That is exactly what you're saying, bolt from the blue. And then Dr. Lyons actually added bolt from the gray, because it may not have cleared up all the way. It may have stopped raining and things look calm. But, there might be some cloudiness in the sky and then bam, so it could be a bolt from the gray. They're trying to add that term.
Bolt from the blue just rolls off the tongue better, I guess.
No, it's, everybody's, yeah.
I want to go back to the type of lightning that this is, because there are different types of lightning, right? Like there's cloud to cloud and within cloud and cloud to ground. Can you explain what those are and how this fits into those descriptions?
So with the lightning, it's basically taking advantage of whatever path it can discharge the quickest. And a lot of times when you get that separation in charges, it will happen within the cloud. And then to have it happen on the ground, you need a little bit more. It's a little bit more challenging because instead you're in the cloud and you can discharge, but now you have to go through air, right? So air is going to have a ton more resistance than just going through the cloud itself. And you tend to see the cloud to ground strikes after the storm has gotten itself going. It's very rare that you see a burst of cloud to ground lightning at the beginning, but at the beginning of when it's growing and, you're starting to see lightning, it's typically going to be from there. But it's not to say that it can't happen at the very beginning. You always have to be aware that both types can happen at any time. But there seems to be a preference in the timing of when you see the cloud to cloud versus the cloud to ground. And then the bolt from the blue that you're talking about, that does typically come towards the end of the life cycle of the thunderstorm.
Can those be dangerous to like airplanes where they're avoiding a storm? So maybe they think they're not near the storm, but they can still get struck by lightning?
Right. And for the most part, from what I know about the engineering part, that aircraft can withstand that even with the sensitive electronics. But there are definitely instances where they get hit and they land and you can see exactly where the lightning bolt hit the fuselage or, the wing or even the engine, and things like that. But, with the metal casing, you can distribute the charges. It just depends on how strong the lightning was that hit it. And it's same with humans too. I mean, you probably wouldn't, it's one of those things that, you got to be careful how you word it, but lightning, most people do survive. The issue is the polarity of the lightning and then how much what we call the peak current, like when you stick a plug into an outlet, there's like 10 amps or 15 amps, but lightning delivers thousands of amps or tens of thousands of amps in a split second, right? So you can survive that as long as, number one, you're dry, you're healthy, and the peak current is not so high that it overcomes your own internal resistance. It's not to say you're not going to get hurt. But as I tell my students, it's like, do you want to get hurt or do you want to die? That's the thing. And a lot of times, people have to be resuscitated, from that when they do get struck. But it's such a fraction, in a fraction of a second, because with my lightning mapping sensors, I can track the entire path of the lightning from beginning to end. And it sits in a time window, so I can have all of the lightning points in that window. And then you look at time A and time B, and it's like we're talking about half a second, if not half of a second or something like that. Just something ridiculous. And all of these source points, are sitting right there. So it's amazing, the resolution that we can get on this and then the time it takes for that actual flash to happen. Is
it really 1.21 gigawatts?
Oh, dude, yeah. Well, I don't even know where they came up with that. So for us nerds, right, that's a funny play on something called Ohm's law. So yeah, I don't know how you would generate 1.2 gigawatts. I'd have to sit there and think about that. Or just
do people ever call you Doc Brown?
Yeah, for sure.
I immediately, the first time I met you, went there.
Yeah.
Okay, so let's talk about, you've got your network. What does it look like? Are they high up, like detectors? Are they low to the ground? Are they always operational? Or do you have to turn them on when the storm's coming? How does that work?
Oh, it's running 24 hours. They are just basically like radios. They're sitting there listening for a certain channel. So again, I joke with my students because I remember the horror of having to plug my Atari and Nintendo into the TV and turn to channel 3 right? No one knows what channel 3 is, but it's an unused frequency because everything's gone digital. So we use that particular frequency to listen
Oh.
for lightning. And kind of similar to how on a radio, when you hear the crackle, like AM radio, that's another joke, right? Everything's streaming now, so nobody listens to AM radio. But the crackle that you would hear on AM, right, when you're near a thunderstorm, it's similar to that. So it's detecting all of that and processing the signal into an actual lightning source point. We call those source points. And then you just grab as many source points as you can every time step and then turn it into a lightning flash. It's a bunch of computer software that's running, but it's a radio. It's listening. It's not putting anything out. It's actually listening. So if at least four can hear the same lightning bolt, then they will try to triangulate or geolocate all of those signals. And then, like I said, I can display it on the screen. The website runs continuously. So it's whether it's clear sky or not, it's listening for storms. And once the storm happens, then you'll see the screen start populating with a bunch of dots. And if you're under all of those dots, you're in trouble.
Is there a way to give this information to the public in real time in a warning sort of way?
The short answer is not yet, but that's something that is being taken into consideration because the National Weather Service is speaking about this, using, and I'm trying to get in on this for sure, but using lightning in an operational sense, because right now you have the radar, which, gives you a lot of information about precipitation, storms, things like that. But the added advantage of the lightning is that uptick in lightning activity or downtick, sharp uptick or sharp downtick is usually related to severe weather and flooding. So I'm able to show this. And that's what I plan to do on my website, is starting to throw out warning messages to, just we see the uptick or the downtick, and then other factors that I look at just with the data that I can get from my sensors that I can tell in many cases, if, before the radar that, storm's about to get organized, it might drop a funnel or something like that. But right now we haven't gotten to that point. Because again, if you have an uptick in lightning, you might get a storm. If you have a downtick in lightning, you might get a storm, but it's for two different reasons. So it's one of those things that it's moving in that direction. It's not there yet.
Okay, question. If it is indicative of flooding, does your network cover the part of Texas that was impacted by the severe flooding last July? And if so, was it something that you noticed a connection there? Since
it's a TV channel, the drawback to using such a high frequency is that the further away you go, the less of the signal that you will see, at least on the ground. So answer your question, yes, I did see the lightning in Kerrville, but not as much because it was far away and that lightning was a little bit higher up off the ground. So I'm losing my signal the further out that I go. And I'm trying to actually install other lightning mapping arrays that kind of link to Houston.
Okay, and then as far as detecting from above, going back and looking at old satellite data, is there any work being done with using AI to detect these? I know that when it comes to satellite analysis, sometimes AI is being used to look at old satellite images. Is there any work being done there?
Yeah, for sure. For sure. And, and that's actually the newest, kind of proposal call that's going out, is how to put AI into our techniques, to get data. First of all, recognize that this is a long bolt and then have the computer, train the computer on that. And then figure out what's the average length and what's around the time that you would start seeing those, or follow the actual core of lightning as it moves and then project its path and maybe how strong it's going to get, or maybe if it's weakening. So that is definitely something that's underway. The only issue, because all of these detection platforms have pros and cons. First of all, the satellite's 20,000 miles away, right? So it's good that you can get that vantage point to see, the entire, disk of the earth and then zoom in on storms. But for the lightning that's going to happen close to the ground, satellite's not going to see through much of that cloud. It's only seeing the stuff that comes out, all of the photons or all of the light that comes out of the top of the cloud. So if you got lightning in the middle or under, then you're missing that data, and that actually will trip up your model. So these are the things that we have to be aware of, that AI needs data, and the more data, the more confident that you can be. So that's why we try to put all of these, things together. They're all complement. Nobody's competing. It's kind of like a complementary thing that we can do.
Yeah, for sure. Have you noticed, as an atmospheric scientist, have you noticed any sort of like correlations with megaflashes and what kind of weather systems they tend to occur, or time of year, or part of the country?
Yeah, and the people I'm working with actually collaborate with scientists at Georgia Tech, and they have a few studies out already. The last, I guess, 4 or 5 years, they were cataloging that only because of GOES, like the satellite, that they could see the mega flashes. And there are preferential regions on Earth where you see them a lot. Houston's one of them. So surprise, surprise. Houston and the surrounding Gulf, and then Africa would be the other one. So again, it's these storms that kind of explode and have these big cloud regions. So you get the thunderstorm, and then the cloud spreads out, and then all the charges spread out with it. And then that's when you can get the mega flashes to show up.
What is your like personal relationship with lightning? Are you like a fan? Are you scared of it? Do you have a history of some sort of trauma with it?
Yeah. So yeah, I was one of those. It's kind of like, if you're asking somebody, why did they want to be a fireman? Or how did they get into doing that? And the first thing they'll say, well, I was afraid of fires for a long time. So I was afraid of lightning for a long time. And then once I got over it, it was actually pretty cool, because you can see how it branches out, and, you just pay attention to it. But at the same time, you definitely don't want to get too close, when you're looking at these storms. But that's basically what fascinated me, is just how it branches out, the different colors. Like a lot of times you can see that. And it stuck with me as I was growing up, since I was a kid up until now. So I don't actually study why they're different colors. I have some idea, but that's like the physical end of lightning. I do more of the operational or application part of it. But I love physics. I love chemistry. It has a lot to do with the physics and chemistry of the atmosphere, why they're different colors. But I just didn't decide to go in that particular direction. All of us lightning scientists, we're niche. We have our own little niche. And then we just really come together and then show each other, okay, I got this part, you got that part. So it's like a puzzle piece that we all bring together. So it's really cool. It's really cool.
So there's like a lightning expert that does colors, and you like hang out.
Oh yeah. I mean, when I first started here, so Dr. Orville, who was the lightning guy before I got here, and then I inherited the lightning network from him. But he was looking at, so if you take a camera, let's say, so you have you have your camera lens right here, and you put like a glass, what's called a diffraction grating. So it's made out of glass, and you take a picture of it. You can actually break that bolt into separate wavelengths. And there's always equations, but there's equations that you could use to solve for the temperature of the lightning based off of the color, right? So that's one of the things that he worked on a lot. And there's all kinds, there's scientists that flew some airplanes out over the Gulf a couple of years ago looking for gamma radiation. So whenever, I joke with my students like that. So did you know that you can get X radiation, gamma radiation, you could be the Hulk, right? Because isn't that how, you could be a Marvel superhero or something like that. So yeah, it's a lot of things that come out of it. But again, we didn't know because we didn't have the technology. And now, like, people are studying all aspects. And I do what I call space lightning too. Not the lightning that goes from cloud to ground, but the lightning that goes from the top of the cloud towards space. So I'm definitely into that as well. I told you I wear many hats, but
Yeah, how does that happen?
oh, dude. So and this is something that until recently, just from working with this for a few years, that was blessed with some really good students who could take good pictures, right? But it's one of those things that people think that it was happening all the time, but couldn't really prove it because we didn't have the visual evidence. But all of the lightning that happens, you can't ever get something for nothing. You have to account for basically every electron, every photon, because the equations say so, conservation, things like that. So anyway, not being too nerdy, there's a fraction of lightning that was never accounted for in any of the models or any of the equations because we couldn't see it. Now that we can see it, we can start filling in the gaps. And it's the lightning, they're called transient luminous events, so TLEs. And they could be red, they could be blue, sometimes green, different colors, depending on what type of event that it is. But they're the ones that come off the top of the clouds. And just check this out. It showed up in literature, I think, since the Renaissance, maybe a little bit after that, in the 15th, 16th century or so, that you have these paintings that have these tendrils or things like that coming up from the top of the clouds. And nobody knew what it was, but you're looking at the night sky and there's lightning in the background and you see all of this activity going on above the cloud. Of course, it looks weird or strange. You're probably going to do a painting of it or something. But it wasn't until the 80s when you had Air Force pilots that saw them as they're flying over the top of the thunderstorms. They're really flying, really high up. So they saw them, and that was the first time that we actually had visible evidence. And in that 5-year stretch between the mid 80s and the early 90s, anybody and everybody with a camera was out there looking for them. So there's a bunch of studies, in the late 80s, early 90s on this phenomenon. So, and it turns out we see them all the time, but again, we used to think that there was a preferred time that they would show up. So it's like basically wait for the storm to start dying down, kind of like with the megaflashes. Wait for it to start dying down. Wait for it until it's on the horizon. Well, my students were out there at every part of the storm, and they were getting them all the time. They were getting them at the beginning. They were getting them at the middle. They were getting them at the end. So we have to redo a lot of the ways that we think about that. And then really quick, what I'm working on with Georgia Tech is a way to kind of observe them at the different wavelengths. Because we can only see, was a Roy G. Biv, right? We can only see in the visible. Well, what about the lightning that you don't see? Because it's not to say that there's nothing out there it's not always going to be visible. There might be something out there that's either, ultraviolet or infrared that we can see, because we have to account for that. It's a conservation law, and we have to account for every bit of energy that's being passed from one area to another. So that's what's going on. And I think that's one of the coolest things. But like I said, I'll leave that. I've taken pictures of the sprites and the jets and all that. They've always come out fuzzy. I'm terrible at taking cameras, so I just gave up. I let my students.
What's the goal here with your research, or is it kind of like a research phase right now, or is the goal to detection, like save lives, to transmit this data to people who are warning?
It's twofold. So there is a science component, because that's what pays the bills, right? Nobody's going to pay me to go out there and chase. But then the operational end, for sure. I want my website to do something more than just say that there's lightning in the area. I want it to spit out messages. I want to have markers tracing the storm and then following it in near real time, because every minute it will update. But using that kind of resolution scientifically, then you can link what's called the electrodynamics to the dynamics. But the issue is I can only do this in that range of Houston until I can get more lightning mapping arrays across the state. But you can only do it around that. So let's say NWS Houston, Lake Charles, Corpus Christi are the immediate, what's called county warning areas, or the immediate offices that are within the HLMA, the domain at HLMA. So I'm constantly tweeting to them saying, hey, you might want to pay attention to this storm, but only because, the lightning rate looks like it's going up. And a lot of times what will happen is they'll put a polygon around it once, within a few minutes of putting a tweet. And not just over land, off the Gulf, they have an extent, certain amount of miles out over the Gulf, and they can put another polygon because there might be offshore rigs there too. That might be the path of that. But if those storms are showing rotation, which now that's what I'm getting to with the science part, we can use the lightning kind of to say, hey, this storms are getting a little bit more organized. It might be showing rotation. You're already far away from the radar, but I'm getting enough lightning data that I can make that distinction. And they might put a polygon around that too. So it's the research and the operational end that I'm looking at.
Well, it has to be rewarding knowing that you detected lightning on your network, tweeted someone, and they perhaps saved a life because of it.
Well, it's the best. Again, it's the best we can do. It's like because I work with the emergency management, and where do you deploy your assets, right? I mean, you can know a few days ahead of time that there's going to be some severe weather in the area, but they might need to make game time decisions, right? And this is something that can give them that few minutes. I'm not promising the moon. It's just, if everybody says, if I only had a few minutes more, I could have did this or did that. So that's the best that I can do, at this point. And I think, and, just my opinion, you could try to go for an hour or 2 hours or something like that. But, you're not going to know where you're going to be or what's going to happen. But that few minutes as you're tracking it, you just go with that. I mean, that's really it becomes diminishing returns at a point. So I'm just saying few minutes and we can go with that.
Any goals for what's next with your research? You're going to keep plugging away with what you're doing.
Oh, dude. Yeah. I'm always trying to think 5 moves ahead, but I'm so stuck on the space lightning thing. And now with we're getting this operational because there is a way, if we use machine learning, there is a way to kind of use this to track the storm, how it will pulse up, how it will pulse down, and kind of do some minute to minute predictions on what's going on with that. So I am sticking more towards the operational end for now, but I will, get older and maybe more grayer. I'll get back into the more theoretical stuff. Like, why does lightning actually, kind of zig and zag? It's a nice physical concept. I kind of joke because I want an Aggie ring, right? I want an Aggie degree. And I already figured out if I ever did do it, it would be in physics, and I would study why lightning actually, relativistic and non-relativistic electrons, all the quantum nerdy stuff like Doc Brown. That's something I would do in my old age. But right now, yeah, I'm set. I'm set with what I got.
Well, you just need that time machine, and then you'd have all the time in the world to figure this out.
Yeah, good grief. Go back to 19th century.
That's right.
That was awesome. Yeah.
Off the Radar is a production of the National Weather Desk. Make sure you're following the show on Apple Podcasts, Spotify, or wherever you listen to podcasts. New episodes published every Tuesday. Thanks to John Jensenius and Tim Logan for joining me on the show today. Thanks to the National Weather Desk and Sinclair Broadcast Group for their ongoing support of the podcast, and to Brian Petras for his help with today's episode. I'm meteorologist Emily Gracie. Make it a great day.